We're looking at Z-scores or Z-scores in this video. This is almost a little bit of a historical holdover from how normal distributions were done back in the day. Before calculators, people had these big books, for example, of like sine, cos, and tan values for various angles, or normal distributions for various quantiles. Now, you don't want a table for every normal distribution with every possible mean and standard deviation, because that book would be infinitely long. Basically, they just standardize it. So here's how to standardize it. Essentially, this is the example we did when we did normal distributions. So it's Australian women, you've got the mean in the middle, that's 161. And then every time you go up one standard deviation, so the standard deviation is 7, that's like the next little section on the normal distribution. Anyway, we tend to call these the X scores. X being like the actual amount that was measured. And then we also have Z scores. So the way Z scores work is you just set the mean to 0 and each standard deviation is 1. And then every time you go back, it's 1 back. So those are the corresponding Z scores. So it can really turn any normal distribution into something comparable because the mean's always 0 and then each standard deviation is 1. You can think of like a Z score. It's like how many standard deviations above or below the mean are you. Standard deviation, I guess I'll use a proper symbol. How many standard deviations above or below the mean are you? So that's how you label it with Z scores. There's also a formula for calculating Z scores. So calculate the Z score of a woman who's 170 centimeters tall. So 170 sort of lives in here. So I would expect the Z score to be maybe like 1.3 or something. So it's between 1 and 2. There's a formula for it. So Z is whatever the observed value is, X, take the mean over the standard deviation. So this is 170, take the mean, 161, all over the standard deviation, which was 7 in this example. That's 9 over 7. And we can work out 9 over 7 on our calculator. It's 1.28 or 1.29. I guess my guess of 1.3 was fairly close. 1.29. So that's our Z score there. Calculate the Z score of somebody who's 145. So the formula works even if the number is less than the mean. So 145 take 161 over 7. And that's the Z score there. And we can just work that out. 145 take 161 over 7 gives us minus 16 over 7. Or if we want it as a decimal, minus 2.29. Z roughly equals minus 2.29. And 145 centimeters would be sort of like, here. And yeah, I would expect the Z score to be about minus 2.29 there. That's how they work. You can answer normal distribution questions about it. So if you've got the standard normal Z, so what that means is that Z is distributed normally with a mean of 0 and a standard deviation of 1. You can absolutely just find probabilities. So this probability here is going to be, so we'll go stats, distribution, normal, and CD. The lower was 1 and the upper was 2. The standard deviation is 1 and the mean is 0. So you get 0.136. Cool. And funnily enough, that corresponds to that percentage there between 1 and 2 for the Z scores. Okay. Now, here's where they get a bit more useful. So all that stuff before was like historical context for why we've used them in the past. They're really useful for comparing different distributions. So this is the situation. Alice has done 2 tests and the tests have like different means and different standard deviations for each one. So you'd be tempted to say that her physics result is better because it's 85%, but that's not necessarily the case. Maybe methods was harder, maybe physics was harder, we don't know. So we use Z scores to compare. Sort of like the year 11 version of this would be calculate the probability of doing better than Alice for each. And then the lower probability is the better mark can think about it. Like if it's less likely that you do better than Alice, that means that Alice did better. The Year 12 version just uses Z scores. So I'm going to say Z for methods. Let Zm and Zp be the Z scores for methods and physics, respectively. Okay, so Z with the M is the X value, take the mean over the standard deviation. I guess this is all for methods. So that's going to be, she got 80% on the methods test. The mean for methods was 72. We're dividing out by the standard deviation of 5. So this is 8 over 5, or 1.6 if you want. Okay, Z for physics is, let's see, she got 85% on physics. And then the mean for physics was 70. And the standard deviation was 10 in that case. So Z for physics equals 15 over 10, or roughly equals 1.5. Okay, so if we sort of think about what this looks like on a bell curve, we've got the mean sitting there at 0, and then 1, 2, 3 for the Z scores. Her methods Z score was at 1.6. And her physics Z score was at 1.5. So her methods one was better. She's like further along to the right of the bell curve. That means she's more above average in methods. So methods was better. She is further above average. And I really want to point out that this gets into some subtleties that aren't captured just by your intuition. So immediately you would think maybe physics was better because she got a higher mark. And then if you're thinking like more critically about it, you might think, oh yeah, okay, well, she got 80 versus 72. So she was like 8% above for methods. And the mean for physics was lower. And you would think, because she was like 15% higher than the mean for physics, and then she was only 8% higher than the mean for methods, you would then think physics is better, even if you look at the averages. But the thing is, physics is much more spread out than methods in this example. So every extra 5% that you can get for methods is a lot more substantial than the 5% extra that you can get for physics. So it's not until you factor in her score, the means, and the standard deviations that you can conclude that methods was a slightly better result in this example.